One of the classical predictions of the theory of general relativity is the gravitational redshift, along with light deflection and the anomalous precession of Mercury's perihelion. As a matter of fact, Einstein first derived the gravitational redshift in 1907 and 1911, well before the publication of the complete theory of general relativity in 1915. When light of frequency nu0 is emitted from a massive body, the frequency decreases as it gradually moves away from the body. When the light is received by a distant observer, its frequency is no longer equal to nu0. It's less than that. Hence the name. The color of light has shifted towards the red end of the spectrum. Since light is made out of photons, and since the energy of each photon is related to the frequency of light by the Planck-Einstein formula, E equals h nu, the energy of the photons received by the observer is less than that on the emission surface. We could say that photons lose energy in climbing up the gravitational well of the massive body. But, is it exactly like that? Let's find out. Consider the following thought experiment. We have a system performing a simple four-step cycle. The system consists of a body of mass m, at rest at point B, and a crane at point A, at a height h, above m. We also have a beacon placed at point B that will be used at the end of the cycle. The system is in a uniform gravitational field G. The first step of the cycle consists in the crane raising m, from point B to point A. In doing that, the crane performs a work equal to mgh, which is also equal to the gravitational potential energy now acquired by m. In the second step, the mass m is slowly released back to point B, and its gravitational potential energy mgh is entirely recovered by the beacon and converted into a single photon of frequency nu, namely mgh equals h nu. In the third step, the beacon sends the generated photon to the crane at point A. In the last step of the cycle, the photon is absorbed by the crane, and its energy stored in the crane reservoir. Now, since the system is in a conservative force field, at the end of the cycle, no energy must be lost or gained. Therefore, the energy of the photon at point A must be equal to the energy spent by the crane at the end of the first step, namely mgh. The crane must recover the same energy spent in the lifting process. Owing to the Planck-Einstein formula, this necessarily means that the frequency of the photon at any point between B and A must be the same. Therefore, we have no gravitational redshift whatsoever. This thought experiment is simple to understand and only uses two fundamental principles of physics, the conservation of energy and the Planck-Einstein relation. There is another thought experiment worth mentioning. A closed wagon of mass m moves horizontally without friction in a vertical uniform gravitational field G, at a constant velocity v. Inside the wagon, attached to floor B, there is a particle of mass mb. At a certain point, mass mb annihilates into a photon of energy equal to mbc squared. Then, the photon travels upward toward ceiling A and is absorbed and converted by a suitable apparatus into another particle of mass ma. This particle also ends up stuck to the wagon frame. The whole process happens exclusively inside the closed wagon. No horizontal external forces act upon the system, and no mass is ejected. Therefore, the total velocity v must be the same before and after the whole process, along with the total horizontal linear momentum of the closed system, wagon plus particle. That means that the mass of the particle generated at point A must be equal to the mass of the particle at point B. Since the mass of the particle is proportional to the frequency of the photon from which it derives, the frequency of the photon at point A must be the same as that at point B. If you want to know more about it, please check the links in the description. These results may appear harmless, but they aren't. For example, they cast a worrying shadow on our understanding of one of the most fascinating astrophysical objects. Guess which?